Good morning or good afternoon, depending on which part of the world you're joining us. Very warm welcome to using analytic AI to improve behavioural research. This is being jointly presented by myself, Jana Hastings and Robert West. You can put any questions up in the chat as we go, so please do that and we'll do our best to get through them. And just to say, this is the second of 3 webinars on AI and behavioural research. The first one was on using AI to improve behavioural research with a focus on generative AI, and that's on the website, so do have a look if you missed it. And then we'll have a third one on the 12th of May, responsible use of AI in behavioural research, an important topic, and lots of questions have come in on that. So this is how we're going to run the webinar. I'm going to start talking about the Human Behaviour-Change project, which is an example of using analytical AI in behavioural research. And we've got 3 different question and discussion sections, because we think this is really important to address your questions. And thank you to those who've already sent some in advance. Then I'll hand over to Jana, who will talk about analytical AI approaches, examples and implementation in the Human Behaviour-Change project. And then Robert West on the demonstration of the outcome prediction tool. So we were all collaborators in the Human Behaviour-Change project, Jan Hastings bringing ontological and computer science expertise, and Robert West bringing behavioural science expertise. Okay, just to for those who weren't at the last webinar, or those who were, to remind you, the difference. So generative AI produces new content or data, often mimicking human-like creativity. For example, text, images, audio, or code. And examples are chatbots, answering a question, writing a blog, designing an image. And I hope everybody is making use of this incredibly helpful tool in their research. Analytical AI, on the other hand, classifies and reasons with existing data. So things like data integration, pattern recognition and prediction, and natural language processing. And examples of applications are fraud detection systems, weather forecasting, diagnosing disease using medical imaging. So today's objectives are, first of all, to increase your understanding of analytical AI and how it can improve behavioural research. Secondly, to introduce some examples that we can use, and thirdly, to demonstrate an AI tool for smoking cessation outcomes from RCT findings. Okay, so I shall talk about very briefly introduce you to the Human Behaviour-Change project. Okay, so this was a Wellcome funded, turned out to be, I think, a 6-year project, and it was a collaboration between behavioural scientists and computer scientists. As you can see in the next slide, a very large team over those years. There you can see in the green, behavioural scientists, computer scientists, and systems architecture who helped to put everything together. So the vision of the project was that if we were to develop an understanding of human behaviour to answer variants of what we call the big question, which is, when it comes to behaviour change interventions, what works compared with what, for what behaviours, how well, for how long, with whom, in what setting, and why? Now, none of us ask questions quite so complicated, but if you think of the questions you're asking either in original research or in evidence syntheses, it's some variant of that question, some of those things. However, when it comes to human beings trying to synthesize evidence to answer this kind of question, we just don't have the volume of research that can answer that question. We know when we do human beings doing evidence syntheses, as soon as you have 2 or 3 of these aspects, you just lose the power to be able to answer the question. And in addition, if we had enough evidence that we could have enough power to answer those questions, humans' brains aren't clever enough to detect all those patterns that we need. So this is where computer science and artificial intelligence comes in. Finding huge amounts of evidence, which we won't talk about today, and then also being able to detect patterns and make predictions. So the challenges answering this kind of question on the left-hand side, one of our problems, in addition to often not having enough evidence, is that the research methods and topics are very diverse. We also, in addition, have inconsistent and incomplete reporting of what we're doing. And then when it comes to the research findings, often we have equivocal or contradictory findings and often sparseness of findings. So those are our challenges. Some of the solutions that we addressed in the Human Behaviour-Change project was to, first of all, seek large amounts of evidence, but then structure that evidence and all the things that produce that evidence in terms of the methodology by what's called an ontology, which is a way of representing and structuring knowledge that is consistent, that uses a shared language, and very importantly for today's seminar, can be read by computers. And so what we do is extract information from reports of intervention evaluations and structure them in terms of the ontology classes. Now, I'll show you a kind of bird's eye view of the ontology we developed for this purpose. And then with the research findings, we then can use artificial intelligence and algorithms to predict outcomes. So here in this visualization on the left, you have what we're very used to, our messy evidence growing faster than humans can keep up with. We estimated over 100 intervention evaluation published a week. On the right-hand side, what do we want? We want to turn this messy evidence into well-organized, useful scientific insights. So we want up-to-date estimates of the effectiveness of behavior change interventions. We want to unpack the reasons for heterogeneity in intervention effectiveness, get beyond saying, you know, small to medium effect with large heterogeneity. And thirdly, generate new testable hypotheses about behavior change. And how do we link these two? In the blue triangle, we have our ontology, providing an organization structure for the knowledge that the information we get from evaluation reports, and then using AI, NLP, ML to do this. So here's the bird's eye view. If you look at the bottom left-hand corner, you've got the intervention with the content, which is behavior change techniques, and many aspects of the delivery, mode, schedule, source, etc. Then on the right hand, we've got our outcome behavior. That's achieved through various mechanisms of action or process of change. Now, these are moderated by the extent to which the intervention's engaged with, its reach and exposure to individuals, but also by the context, which we define as the population, the setting, and also events that occur. And all of this in the blue bottom part of the triangle needs to be considered together along with the research study methods to feed into the outcome behavior value. And then we have maximum information that we can use in predictions. So here on the in the red box here, we have what we call the scenario. So any randomized controlled trial will have several conditions. All of these are scenarios that we need to define. We need to specify all of that scenario. And if you look in all of these little boxes, little circles rather, you'll see many of the things that I showed you in the triangle, and they're linked by different relations. And in the blue solid boxes, you see the report, but also the plan. And the difference between the plan, which is often in the protocol, or the report is what we call fidelity. Under each one of these little circles is a many-leveled ontology of sometimes more than 200 entities. On the left-hand side, you have a similar structure for the evaluation. And this is being worked on, developed in a new project that's funded by the National Institutes of Health. Luckily, we got in time. And this is building on the Human Behaviour-Change projects to develop the evaluation ontology and also tools for making this a more easy to use structure. Here we have the website. Do go on it. It'll you can learn much more about the ontology, how to use it, how to search and visualize it, etc. And lots of resources you can find through that. And just finally, before I hand over to Jana, this is really summarizing what I've said, how we can use ontologies to predict behavior change intervention outcomes, which is what we want to do, whether it's policymakers or planners or service managers or researchers. We want to be able to predict for a particular scenario what is the likely outcome. So we have our evaluation reports, we extract data, we organize it with the ontology to produce a database that then we can develop machine learning and algorithms that then can predict intervention outcomes. And the prediction tool will be demonstrated by Robert West at the end. And now happy to hand over to Jana.
Just a reminder that you can add your questions in the Q&A session. I wasn't sure, Susan, were we already going to take a question or two now, or should we wait until after my presentation part?
Well, I'd say since we haven't got any as far as I can see, I would say let's go on to your part. And yeah, we do have some questions that have been submitted that we can address, but do add any more that you have as we go.
Okay, so welcome everybody, also from my side. So in my part, I'm going to talk a little bit more technically about analytical AI approaches and maybe giving a bit of an insight into how this general possibilities that analytical AI offers were then translated into one particular implementation for the Human Behavior Change project, but along the way, hopefully giving you some ideas of other possibilities of analytical AI, given other data sets and problems that might come up. So before I start with that specific case study, I just wanted to do a sort of an overview or think about together what some of the types of predictions that AI has been applied to in the behavioral sciences that I'm aware of or that I've seen reported on in the literature, and maybe you know of some others, but it's really diverse. So for analytical AI, basically the definition is you have some algorithm probably trained with some data, and it's making some prediction, and very often those predictions are completely invisible to us as users or eventual users of such systems. So for example, every time we use an online streaming service or online shopping center with a big company such as Amazon, we are being studied by algorithms, and these algorithms are being used to make recommendations, recommending our next movie or our next series that we're going to watch or the next purchase that we're going to make. I remember in the sort of earlier days of this kind of recommendation analytical AI algorithm, there were some hilarious fails, like recommending Pink Panther as a similar movie to Black Panther. But the technology improves all the time, and we don't see as many of those artifacts. And the better the technology gets, the more invisible it becomes. Similar kind of recommendation is at work filtering our social media feeds. Wherever we have a feed that's algorithmically driven, there is an AI model behind the scenes, and this model is building an understanding of our preferences based on when we click likes and so on. And then it's making predictions of what we would sort of like to see next. And this process of filtering and targeting, it's commercially valuable because targeted advertising. It's also potentially politically having an impact, right? It's one of the algorithmic drivers of our current potential drift in some areas of the world towards different political preferences driven by different information landscapes, which are driven by algorithms. So I think there's, for behavioral scientists, many, many interesting questions at the interface between algorithms and behavior. Another type of application that many of us use regularly is face recognition. We may use this explicitly if it's in our devices and enabled. So for example, when I access my bank account, this is authorized via a face recognition that goes through my phone. But even if you've switched all of that off, if you travel and go through an airport and use one of those automated systems to check your passport, which is now mandatory that everybody uses it, and this is also working from face recognition. So face recognition is an example of an image-based algorithm. The previous recommendation systems, these are more kind of knowledge graph-like. They're driven off this big heterogeneous data sets, which are having different types of data in them, movies, preferences, and so on. Coming to the more research-oriented types of application, as Susan mentioned, we will talk about the Human Behaviour-Change project in more detail as a specific case study, the prediction system that was built there. But other kinds of AI, analytical AI, are also becoming ubiquitous throughout research as a kind of methodology. And here, for example, you may have new forms of measurement which enable you to track or understand behavior through a different lens and in a finer time scale, thanks to the AI capabilities that allow such data to be analyzed. And for example, there's a whole sort of area of research studying physical activity directly through measurements which are done with for example, wrist-worn activity sensor. And all of this kind of making sense of this kind of data depends on AI algorithms. At the same time, you may have language-based AI, which is being used to interpret content from your user in a study or from online users. But this language-based AI is not being used generatively. You're not interacting with it in a chat-like way. You're using it to categorize your data, to make ratings about or assign members of your study, were they happy, were they not happy, this kind of predictive task, which is being completed by analytic AI. And finally, you may be supporting your research methodology with other modalities, which are also only accessible to AI algorithms. For example, you may have image-based analyses, such as location photographs, which you are using to try and understand better the context in which behavioral choices are taking place. Maybe you've got photographs of the environment around the shop or trying to understand the contextual settings. So this was just a very high-level overview, and there's, of course, many more that are not mentioned here, but the point that I would like you to take away with you is that AI is all around us already. It's driving many aspects of our modern world and digital world, and offers many new research possibilities, which are also exciting, potentially allowing us to study things with more contextual sensitivity and relevance. Okay. So as I mentioned the previous webinar, and for those who didn't attend that one, I will just briefly repeat, there are different historical families of technical approaches to develop AI algorithms. One big family is learning from data, machine learning, and now we have models which are really very huge, but they're still based on learning from data. Another family of approaches is where humans, so-called experts, specify the rules which the system has to follow. They sort of define the knowledge or the rules or the behavior of the system explicitly. And the system is then able, using logic and various other inference capabilities, the system is able to act intelligently based on this rules and knowledge which it has been given explicitly by humans. And there are strengths and weaknesses of each of these approaches. the main strength of the learning from data approach is that you don't have to say how the system should behave. You can just learn from some examples. And this, of course, matches the situation in the real world where we don't know how we want the system to behave. We want it to figure out what the rules are. But on the other hand, there may be some things where our data is incomplete or can never teach the system what we would want it to learn for various reasons. And in those situations, it's actually more helpful to have experts saying what the system has to know and how the system has to behave and how it has to learn. And for that reason, given these kind of different strengths and weaknesses, what we were aiming for when we implemented the AI system for the Human Behavior Change project was a system that could take some of the best of both of these two worlds, that could learn from data, but at the same time to be able to incorporate some of the expert knowledge, especially from the ontology and from the types of relationships that we knew, and thereby supplement what the system could learn from the data in a situation where the data was not fully comprehensive of every possibility. And of course, data sets are always somehow limited and somehow imperfect and partial. So in order to achieve this, again, just mentioning the data set that we used, we had this research report extracted data set and the ontology providing the structure and the rules. And our objective was to predict an outcome of randomized controlled trials of smoking cessation, and smoking cessation having a very specific sort of standard outcome measure for trials of interventions, which is the percentage of cessation. We then built a system which was able to take this kind of data as input together with the ontology as knowledge and rules and learn from the data set. And just to take a sort of a brief but more detailed look at what the data set actually was or consisted in, you see here an example. The data set are reports of published trials of smoking cessation interventions. These reports are published as PDFs. One of the great frustrations or ironies of doing this kind of work is that we sort of have these beautiful data tables at some point in a research process, which are then transformed into this beautiful but quite difficult to navigate computationally PDF format. And then we have to somehow, as researchers working after the fact, work again to get all the numbers and values out of this beautiful PDF format, which is not very accessible computationally, and turn it into a data set again. But you see here some examples of the kind of information that is being extracted, and crucially for our purposes, extracted in a controlled fashion, because we're using the ontologies that have been built for all these different aspects of a study description, as Susan introduced. We're using these ontologies to provide the feature types for the extraction of data. So we get feature types in terms of mode of delivery, and these sort of detailed level of hierarchy is then associated with the exact features of each study one by one. And you have different types of annotations. Some are quantitative, some are categorical, some you're only interested in was that there or not a particular intervention type or so on. So then for the technical architecture which we used a system which is based on the idea of rules. So rules have the form where you say, okay, if this and this and this condition holds, then do something towards the outcome. And they are naturally interpretable. You can understand all the rules. You can read them as a human, which gives them this great advantage of being transparent and interpretable, which a purely data-driven system usually doesn't have. What we did was we built a system where each of the sort of features that you could use in the rules were linked to an ontology class, and that way you had also a definition and a meaningful kind of interpretation for the ontology class. But So we were able to integrate the features of the rules together with the semantics, but we also added, sort of made a hybrid such that we could learn the weights of the rules, so a quantitative aspect, how much each of the rules would count towards the eventual predicted outcome in a kind of analytical AI way, that we could learn that from this big data set, which we had collected of trials that were extracted from the literature. And as a result, the system is not a purely rule-based system because it also has a learning part. And I won't go into this slide in any great detail, but this is just a schematic illustration of the architecture of the system. Basically, we have a whole lot of different rules. They have weights, which are in the beginning randomly initiated, and then through a machine learning training approach, we are able to find the optimal weights for the rules such that each prediction is having the overall highest performance in our training setup, and we can identify the rules which are most applicable to give best performance for the system over the whole test scenario. So this was a system which is an AI system. We developed the architecture. It's based on other similar architectures, but was innovated specifically for this use case. And the result is you get rules which look something like this, which are combined together in order to produce your eventual prediction, depending on which features you specify as you want an AI prediction for. So, for example, you may be interested in the feature whether there was or was not a pharmaceutical company competing interest, whether there was or was not problem solving as a behavior change technique, and so on. And each of these have the potential impact of raising or lowering the eventual predicted outcome in a certain way. And we were also able to show that using the ontology and deriving knowledge from the ontology allowed us to force these rules or to constrain these rules to be shorter and more interpretable relative to a pure rule learning system without an ontology combined with it. Okay, so this is the system that we eventually built for the Human Behavior Change project. It's interpretable. It's based on rules with weights, as I explained. It uses knowledge from the ontology together sort of with learning from data with this extracted data set. And in the end, when you use the system, when you use this trained model, you can get your predictions with a transparent explanation. And this distinction between kind of a black box system or a transparent one is increasingly important in the world of analytical AI, which is pervasively around us at all times, doing all of these sort of things. Most of the time, we are not told what the basis is on which an AI system makes its predictions, and we are not given this kind of transparency. And if we would be given this kind of transparency, maybe we would choose differently whether we're using the system or not. But that's all for my part, the somewhat more technical part. And at this stage, I think we could already take some questions if there were some, and have a bit of discussion before I hand over to Robert.
Thanks very much, Jana. Yes, that's a very important point about actually understanding what's going on. So with the Human Behaviour Change project, our first computer science collaborators was IBM Research, based in Ireland. And from the very start, we said openness and transparency is an absolutely key aspect of what we want. And so, yeah, I think that's important to bear in mind. Well, we've got quite a lot of questions coming in. I suggest we take a couple each. So Robert and Jana, have a look and see which you'd like to take on. I'll just take on a couple of them here. Emma Ward says it'd be really helpful to have a guide directory of AI tools that can help researchers. Does such a thing exist? I don't know if it does exist, but we have plans within Behavioural Research UK to do exactly this, to have a repository on the website, which will not only have tools and commentary on tools, and they're being released and updated very rapidly, but also have training resources and other relevant information. So we're on that. Also from Dougal Foster, asking about identifying reasons for heterogeneity. And just to say something about, I suppose, understanding behaviour, one of the things we do is develop a theoretical understanding of behaviour and behaviour change. And there are two broad types of theory, explanatory theory. One is about how does behaviour change? What are the processes of change? But the other is about understanding variation. So as we all know, the same intervention works differentially for different populations, different settings, different behavioural outcomes. And so often when we try and gather knowledge about behaviour and about behaviour change, we don't have the power. We don't have the power in terms of scale, as I said, or in terms of speed of processing, or being the ability to process complexity to really unpick that heterogeneity. So this is why I think it's very important. And what Dougal says here is, how necessary is it? Isn't all we need a mapping of heterogeneity so we know what factors predict variation in outcomes, and then we can use them, for example, in post-stratification? And I say yes, yeah, that's exactly what we need, and that's what I mean by understanding variation, heterogeneity. I just think in terms of our potential to be able to generate research and be able to apply research from what we know to new scenarios, which is for most policymakers, planners, practitioners, etc., what they want to do, they need to be able to understand to what extent can we generalize from evidence that was collected in other scenarios to my particular scenario of interest. And this is what we were trying to do with the Human Behaviour Change project. Okay, Robert, can I first of all turn over to you to address a couple of the questions that we have?
Yeah, sure. So David Shipworth asked a very important question, which is around the extent to which the sort of ML approach gives better results than more traditional sort of regression type approaches when you're combining data from studies and so on, or even within a study. And there have been a few, I'll tell you our experience with the Human Behaviour Change project, but before doing that, I'll say that if you look in the literature at various ML approaches to analysing data, you will often find that they don't outperform simpler regression models. By the way, regression, linear regression is itself considered in computer science to be an ML approach, just a very simple one. But other ones that you will find out there, if you just do a Google search or a PubMed search, are things like random forests, and there's a number of sort of deep learning type systems out there. But in many cases, either they haven't been tested against a simple regression approach, or they haven't necessarily done better. And in some cases, they have. There are reasons for using an ML type approach rather than a simple regression approach or meta-analysis type approach anyway, which I'll go into when I talk about our own case. But one of them is that the ML approach basically, especially the way that we've done it with a semantic hierarchy of constructs. So, for example, if you know you've got nicotine patch, that's a type of nicotine replacement therapy, which is a type of pharmacotherapy. You can take advantage of that semantic hierarchy to use every bit of data that you've got. Whereas when you do regression approaches, you've either got to have some missing value imputation or just not use data if it's not available on a particular variable. But in our case, yes, we do find that the ML approach does better than the more traditional regression approaches, but there's a really important other way that we do things with AI and ML when we're making predictions that's different from how they're traditionally done in meta-analyses, for example. And that is we're genuinely making predictions, and we use a thing called cross-validation. So the acid test for a good prediction tool is not how much of the variance it explains in your data set, which is the traditional thing. We talk about R-squareds and so on, but how closely it predicts an unseen data set, the result of the values in that. And that's a much, much harder thing to do. And that's where all the sort of disciplines and technologies around ML, I think, come into play in the experience of people using ML, where you've got things, traditionally things like overfitting, if you've got too many parameters, and there's a lot of craft associated, I think, with building good ML systems that work for genuine prediction.
Thanks, Robert. Jana, should we go to you?
Yeah, I would just add one point to what Robert said, which is that depending on the amount of data available and how clean the signal is, some problems, it just wouldn't be possible to get much out of a machine learning approach because there's too little data available and the signal. But if the signal is very complex and you have a reasonably sized data set, then you will start to see machine learning outperforming your more traditional approaches. And this sort of is a good segue to a question by Hannah McCarthy, who asked which algorithms are typically used for the physical activity tracking data. So here we can distinguish physical activity tracking data. There are lots of different systems doing this. And then you can distinguish between algorithms which operate on the raw data, so the signal from the accelerometers and the various sensors which may be embedded in such devices. And to work with this raw signal, you need a deep learning algorithm. It's too complex to do anything with a simple algorithm. But typically there would be some kind of summary information which is extracted from the device, and this is then processed data rather than raw data. And this processed data is typically what researchers work with. So researchers working on activity like studies will work on what was the maximum amount of activity in a given day or something like that, which is a summary information. And you can use various different algorithms to work on that. That was one question that I saw that seemed to have my name written on it. Another one I see, which I would like to discuss briefly, and maybe the other panelists will also have a response, is from Jianyu Chen. Does the invisibility come from the machine deep learning where we don't understand the algorithm? So I think when I talked about the invisibility of analytical AI in various of our processes and interactions with the world these days, I wasn't primarily talking about the opaqueness of deep learning, but rather the fact that we're not always told when there's an AI algorithm operating, when we're using a social media platform or a online shopping interface, or even just interacting with a website like a news website, and something is tracking and it's making suggestions. We're not always told that there's an AI operating and doing these things. Now, it is also true that you may have some algorithms where you can't get a good idea of why they're doing what they're doing. But quite often, for analytical AI, you could have actually some kind of insights into why they're doing what they're doing. And nevertheless, we are not given those insights. And that's what I meant by invisibility of AI at this moment, at this point in history. And this is a problem more for regulators than it is for technicians, I think.
Thanks, Jana. Okay, I'm going to take one here, which is how can early users or early researchers overcome the challenges with embarking on using AI with less understanding of underpinning principles and traditional analytical processes contained in the algorithms behind AI analytics. And I think this is probably a question that applies to a lot of us. And I'd say two things. One is, I think it's really helpful for behavioral researchers to get an understanding of the types of AI, how it works, general principles, and obviously one can pick it up from webinars such as this, but also resources that one can find on the web. And as I said, we will begin developing a repository of such resources for behavioral researchers. But the other thing is, obviously, knowing the limits of one's own expertise. So speaking personally, I have an understanding of the basic principles, but not at all of the technicalities. And this is why interdisciplinary collaboration is so important. With the Human Behaviour Change project, the reason for it was I became very frustrated by trying to do evidence syntheses to address policymakers' questions, either when I was working on a UK guidelines on NICE, our NHS evidence-based guideline body, or collaborating with the Department of Health as a consultant to them, and realizing that because of the speed, because of the scale, because of the complexity, we needed to bring computer science into the picture. But I didn't know anything about it other than the basic principles. So it was very much, I spent probably more than a year tracking down collaborators for that project. So I would say the key thing is to find computer scientists who are interested in working with you. And certainly we had the head of computer science at UCL as a co-investigator, and he had a range of masters and PhD students who were really keen on having projects that were addressing real world problems. And so, this is a really great basis for collaboration. So I would say if you're researchers, do contact, your local computer science or equivalent departments. So Robert or Jana, I don't know if you've got anything to add to that particular question.
So I think the most likely scenario that you're going to encounter where you could think about using AI is actually going to be in analyzing your own data sets. For reasons that I'll go into a bit later on, evidence synthesis using machine learning and ML, and actually Jan has alluded to this, is at the moment quite tricky for a lot of domains, simply because of the size of the data sets that you can put together. And unfortunately, the way that they're reported, which is often quite poorly and idiosyncratically, which means that it's quite hard to construct good data sets that are amenable to ML. But if you've got a data set yourself, let's say it's a large survey, or if it's a randomized controlled trial with many different features in it, then what I think people are increasingly doing is turning to ML to help them to analyze and understand patterns in those data that they couldn't have done with more traditional statistical tools. And in fact, there are lots of libraries out there of commonly used ML approaches which you can mess about with and get some familiarity with if you use R or Stata or even, I think, SPSS. So it's worth, I think that's probably where, if you're new to this, you're gonna find your entry into the system. And if you've got a very large data set and you think there may be some complex interdependencies among various factors and how they link up together and how they associate together, then ML may well be, the way to go about it. But as with statistics, you can You've got to know what you're doing. And I have to say, there's lots of very, very good YouTube videos on machine learning, on the different types of machine learning and so on. But it's still a little bit of a dark art. I mean, Jana will, I think, either correct me if I'm wrong or be able to expand on it. But one of the things I find is that if you're looking to understand patterns in data, or make predictions of one variable given a whole range of variables that may be interacting in complex ways, then choosing the right ML approach is often, involves a certain amount of trial and error. I'm not sure yet that we've got a sort of like some meta rules. I know people are working on it, but some good meta rules for saying, right, in this kind of situation, then this kind of algorithm is going to be the one for you. What do you think, Jana?
Yeah, I mean, I think there's some truth to what you're saying, and there's in some cases an empirical aspect, but in other cases you can have some strong expectations. So depending on the nature of the relationship or the outcome that you want to predict, depending how it's shaped and how much variance there is in the predictor variables and so on, and how this whole looks quantitatively, you can say this algorithm or that algorithm would be a better fit, right? So there are some, let's say, guidelines, but then within the nitty-gritty details, there's often areas that we cannot say in advance, where it really becomes empirical. Will a certain weighting scheme or another weighting scheme get a better result? We just don't, because we can't hold the complexity of the data in our head, we need to sometimes have a empirical approach. And this becomes more and more relevant as the data set become bigger and bigger and bigger, which is, of course, one of the advantages of complex machine learning approaches, that they can handle these huge data sets, and we can then discover things that we could not have predicted in advance.
Thanks.
I would also say, sorry, Susan, just to add to that, also, I alluded to the idea a bit earlier that even things like linear regression are construed in computer science circles as a form of machine learning. They are, but there's a machine learning ethos that goes with it that we don't typically do when we're analyzing statistics, but we should do. And that is particularly around the idea of cross-validation and training sets and testing sets. And I think the more we as behavioral scientists can get into our heads that routinely, if we're genuinely interested in understanding our data and making predictions from them, rather than doing, even if we're doing a linear regression, rather than saying, oh, look, I've got a beta value of 6.2, p of less than 0.001, and I'm explaining 50 or 60 or even more % of the variance, job done. Not a bit of it, not job done. You could be explaining 90% of the variance, and you come to an unseen data set and you do a really poor job. So getting it into our heads to use sort of the machine learning ethos of training sets and testing sets when we're analyzing data, I think would be a big advance.
Thanks, Robert. Okay, I suggest we do one more round of questions and then go on to Robert's presentation, and then we can come back again to other answering questions and discussion. So going back to an early one, Hannah McCarthy said, is it possible to please have the references relating to the first example of the research and investigative methods, e.g. systems for tracking and measuring behaviour? So I'm not quite sure what that refers to, but just in terms of the Human Behaviour-Change project, I should have said that all the publications are open access on Welcome Open Research. So just go on to Welcome Open Research, Human Behaviour-Change project, and you'll find more than 20 publications there. And I think Jana did say something about measuring behaviour. So it may be that it's already covered. I don't know, Jana, if you want to say anything more.
I didn't add any specific references to that section. Maybe we can take that as sort of a, I mean, I'm aware of some research that uses those kind of approaches, and I would be glad to provide some references for the examples that I listed after the.
Okay. So we'll add those to the slides, and then the slides will be up on the website. I also should add that we did do a previous webinar on ontologies, what they are and how to use them. So if you're not familiar with ontologies, which is an important part of the equation here, do go and have a look at it. I thought I would just take a question that came in advance. We got several in advance. And this is from Thomas Mickelson saying, using AI for research could result in one-directional thinking, since AI is basically about pattern recognition, ? So others may know what you're trying to get at, but you know, when I presented this complex, the big question as I described it, this is all about how do you think in multi-dimensions simultaneously rather than one dimension. So, you know, often when we're trying to address questions, we only are thinking 1, 2, or 3 dimensions at a time. But, you know, I would say AI allows much more complex multi-dimensional thinking. But it may be that I've misinterpreted your question. So over to Jan or Robert, if you think there's something else that Thomas was trying to get at there.
So I could add one point. I think in the situation where we're training models based on a whole lot of sort of historical studies, and then we're using this kind of model to help us plan future studies, there is a tendency for the model, because it's trained to predict things that are likely or probable, to sort of shift potential possibilities towards the more common possibilities. I think it depends on the type of the AI, it depends on the type of training data and what you are, how you're using it. But it could be that this is the concern that's being raised. And certainly if we're talking about using generative AI to support the design of a study, we should ask ourselves whether the model, the way that we're prompting the model and the way that we're using the technology is generating the full range of possibilities, because the model works from likelihoods across what it's seen before. On the other hand, I think that the number of the sort of scenarios where this could really result in a restriction in the research space would be relatively few. So many times we could use the technology in such a way that it doesn't restrict, but amplifies possibilities.
Thank you. Before I go to Robert and then Jana for another question each, there's lots here to choose from. Just to say, in the chat box here, Sancha Martin is very helpfully putting links to various resources in answer to some of your questions. So do have a look at that. Robert.
Yes, so John O'Neill put a question in about whether we've yet come to a point where we can make firm conclusions about the limitations of generative AI and analytical AI within the ecosystem. I think we're a long way from that, because part of the reason for that is it's developing so quickly. The tools that are available to us are just growing, well, I don't know about exponentially, probably more than exponentially. So, for example, I've just recently come across a generative AI research tool that you may want to have a look at called Undermined, under MIND, that does a similar kind of thing to elicit.com, which we talked about in the last webinar. Check out elicit.com and Undermined. What we're seeing here is a whole range of products that are coming on at the market, which can support us in different ways. And the problem I'm finding with these is that each of them I'm paying for a pro version so that I can really explore their possibilities, and each of them costs between 10 and 20 quid a month, and by the time you've sort of done 10 of them, it's getting a bit pricey, and so we're going to have to find which ones we find most useful. At the moment, for me, for the Gen AI, it's probably Elicit still, but this will change. So it's changing all the time. The abilities of these tools is changing all the time, and they are responsive to user needs. One of the big ones, I think, that we're going to have to that is still not quite there yet for us, but I'm sure will be, and we can help to support that, is help with annotation. Hand annotating papers to extract information for evidence synthesis is massively time consuming, and we've really got to do a better job. We weren't able in the Human Behaviour Change project to get a really good functioning system, despite a huge investment. They are improving, but they're still not there yet. But part of the reason for that is the way we write up papers. And one of the things that we're doing is to provide people with tools to help them to write up papers that in effect then self-annotate with ontologies. So that's, I think, once we create this new universe of papers that have got the information that we need in the form that we need it, then a lot of that problem will go away.
It's just such a completely bonkers system that we've got at the moment, where we sort of have the information and then we lose it and put it into this published literature where people have to try and retrieve it. I wanted to come to the one question, which is by an anonymous attendee and has had several upvotes, which is, what are the problems and also advantages of using something like ChatGPT to code and theme qualitative data? So first of all, that was not strictly speaking the topic of today's webinar, but rather more the topic of the previous webinar, where we really talked about the use of Gen AI, generative AI, and ChatGPT is, of course, a generative AI. But one point that I can make about this is that in our experiments with this technology and very similar kind of challenges, such as automating the coding of qualitative data, we have seen that the performance varies depending on the topic. So whatever kind of study you're planning to do, if you want to apply Gen AI to that study and automate some part of the thematic analysis and the coding, you have to have some of the information that you have done manually in order to check the performance of the Gen AI system on this particular topic, the topic that you are doing, because the performance varies quite dramatically by topic and by extraction theme. And we also saw the same when we were extracting data out of studies automatically, that performance varies depending on the nature of the data that you want to extract.
Thank you, Jana. I'm aware we got quite a few unanswered questions, but I suggest we go on to Robert's presentation now, and then we'll come back to these questions and no doubt other questions that you have following his presentation. Robert, over to you.
Right, okay. So I'm just going to take you through this case study to give you an idea about what can be achieved, but I'm also going to give you a big caveat because we picked, in a sense, some very low-hanging fruit with our use case of smoking cessation for a number of reasons, which meant that we could do this. And I'm working on another project which is at the other extreme of these features, which requires a somewhat different approach, and I'll mention that at the end. So with the Jana has already given you an idea about what we were trying to do with the in the Human Behaviour Change project, and here's the thing, and it's sort of it's really repeating or expanding what I said a few minutes ago, which is that as behavioral scientists, from a practical point of view, for policymakers and practitioners and people developing interventions, our job is to predict outcomes in situations that haven't yet arisen, haven't yet occurred, even though something very similar might have been tested in another environment. That's no guarantee that you're going to get the same result the next time you do it. We're in the business of prediction. In order to predict, you need to understand. But understanding on its own is not enough. You've got to be able to predict. So when you're using AI and ML, to synthesize evidence from existing studies, you're going beyond what we traditionally do with our meta-analyses, which is to summarize findings and say the average effect size was X, 95% credible interval or confidence interval is, X and Y, and there it is. Nicotine replacement therapy increases quit rates by 50% plus or minus 10%. We're going beyond that. We're saying, okay, in this new situation where to take the example of nicotine replacement therapy, where you've got your stop smoking service in Humberside, your population looks like this. Many of them have already used nicotine replacement therapy before. Their nicotine dependence levels are this, their age profile is this, their deprivation profile is this. What am I going to see if I then provide free nicotine replacement therapy to people in this population? That's what you want to know. And that's what we're trying to do with machine learning. So that's the difference. I can't emphasize it enough. It's predicting outcomes, not summarizing findings. And the problem is that human behavior is influenced by a whole host of things, some of which are measured in our studies and some of which aren't. But even with the ones that are measured, they're going to interact in complex ways with each other. Human behavior is very sensitive to changes in context. So what we're trying to do is to go beyond what is the average effect size from existing studies to predicting what we think is going to happen in what will inevitably be a novel scenario, however similar it might be to some of the studies that have been done where we in randomized trials, for example, evaluated outcomes. It won't be exactly the same. And to do that, we use the behavior change intervention ontology to classify the kind of things that could make a difference to what kind of an outcome we're going to see. And Susan's already showed this diagram. It is our standard HBCP diagram. And what I'm focusing on here are the things that can make a difference to the kind of number that you end up with, which is your outcome value. And so the outcome value here will be a number like 24, 3, 4.2, whatever it might be. The question is, what generates that value? And what generates it will be the intervention. What was in it? What was its content? How was it delivered? What was the schedule of delivery? How long did it go on for, and so on? What tailoring might there have been? The behavior itself, for example, if it's smoking, are we interested in whether people have been abstinent from their quit date for 6 months, or have they just been abstinent at the 3-month period for the last week, and so on? And to what extent they engaged with the intervention? Did they turn up to all the sessions? Did they use the medication as predicted, as required, for example? What's the context in terms of the population? Were they heavily dependent smokers? Did they have mental health issues? What other kind of things might be going on at the time, like COVID or whatever? Was it delivered in a hospital setting, and so on? And also the research methods. So, for example, was it is this number here the result of biochemical verification, or is it based on purely on self-reports? How did we treat missing values, and so on? So all of those things can make a difference to what that number is. So you can imagine it's a pretty tricky task to actually predict what that value is. And that's why we need machine learning to try and do it. So the sort of question you might ask is, here is on the screen, is what is the likely outcome of a stop smoking intervention delivered face-to-face by a clinician or a physician using these behavior change techniques with nicotine replacement therapy in a middle-aged sample who averaged 10 cigarettes a day? Now, you can't really create a model of that kind using a standard regression approach, because you don't know in advance what kind of interactions are going to be important. Is nicotine replacement therapy going to have a purely additive effect, or is it going to have some interaction with 2 or more of the other variables? So you need to have a system which can learn what those interactions might be. And you've got to, as Jana has said, you've got to constrain it so that it can give you rules which you can then interpret. So if you parcel out this question into its components, you've got, what's the intervention look like? Has it got these components? What's the population look like? What's the behavior? And how has it been measured? And that's what we did. And that creates this, you can go straight to this website and mess about with it. But this is the sort of front end of the results of the model that we built using the machine learning approach that Jana told you about. So what you've got on this dashboard is what I'm showing here are a set of population characteristics and other kinds of things about the study. So the mean age, you could set it to 50, or you could, you could set it lower, you could set it higher, and so on. Here is the output. It'll tell you that if you don't know anything at all about the intervention, and and your samples like this, and its follow-up is to 26 weeks, and it's continuous abstinence, and there's no biochemical verification, etc., then in a control condition, you'd expect to get a figure of 4.3. And in an intervention condition where you don't know anything about the intervention condition, just know that it's been called an intervention condition, you'd expect an outcome of 7, which simply reflects the fact that when people are reporting interventions, they don't always report what's in them, and therefore just the fact that it's an intervention could make a difference to the expected outcome. It could also be that in some of these studies they're not blind, so that either the patients themselves or the researcher might be playing a role in elevating that quit rate. But that's the sort of expected value. I'm just going to stop sharing these slides, and I'm just going to change to a live screen where I can show you this in action. I think this is this the live screen? Got too many screens up. Probably this one. PowerPoint slides, smoking cessation contact. Now I'm going to go to. Hang on a sec. Focus. Trying to share the screen. No. Let's try this. Okay, I think that's just these slides again. Sorry about this. Hang on a sec. It worked when I was doing it beforehand. So I'll just stop sharing. Right. Can you see my cursor moving around? Give me a nod if you can.
Yeah.
Okay. Right. So this is the live screen from the website, and you can mess around with it yourself. And the if I do something like add some components to the intervention from the ontology, let's say I add goal setting, problem solving, pharmacological support. And with pharmacological support, I tell it that this is nicotine replacement therapy, for example. You can see that it's added it into this panel here, and it's increased the expected outcome from whatever it was, 7% to about 12%. Okay. And so you're getting a prediction of what the system expects, in this case, the 26-week continuous abstinence rates to be in people who average 10 cigarettes a day with a mean age of 50 and 50% women. And it's also telling you that what the impact of these various different components is to the figure. So is it increasing it? You get a green bar. Is it decreasing it? You get a red bar. Now, what I haven't put in here is who's delivering the intervention. So with the ontology, we can say, okay, what kind of a source is there? Let's say that the source was a doctor, and let's see what difference that makes. And we can see that it makes very little difference. Oh, sorry, it makes a bit of difference. It's just updated. It's now 15.3%. Let's also say, because we didn't know anything about how it was delivered, that it's being delivered face-to-face, and see what difference that makes. That increases it further to about 18%. And you can mess around with this, taking out and adding the components of the intervention content, the intervention delivery, the source, what kind of drug was used, if there was a drug used, what kind of sample you're using, and so on. And so you're using a rule-based machine learning system to predict, if you're creating a service from more than 500 randomized controlled trials and over 1,000 intervention conditions, coded with all this information, you're able to predict with some degree of accuracy what you can expect. Now, there's a lot of limitations to this. Obviously, we're completely dependent on what people report, and what we know is that people don't report a lot of stuff that's in interventions, and they even worse at reporting what's in control conditions. So that makes a difference. We also know that people report things in ways that are often confusing or ambiguous or difficult to extract in terms of information. And we also know, of course, there's other biases in studies in terms of whether people actually even write up the study, if it has got a negative outcome, and so on. But if you've got enough data, with something like this, this is obviously a huge amount of work goes into creating something like this, especially if you're having to do it, annotate manually, then you can build and enhance a model. And this then creates this thing that we're all trying to achieve, which is cumulative science. That model is there. It's now it's not going to go away. You can add to it, you can add new studies, you can add new annotations, and you can improve the model, like ChatGPT-4 builds on ChatGPT-3 and so on. So this is, to my mind, this is potentially the future of data aggregation and data evidence synthesis. However, and I'm going to stop sharing now to give you a couple of caveats. The first caveat is that, as I mentioned earlier, we're using very low-hanging fruit in the sense of we have a single outcome, which is a %, which is percentage of people who are abstinent from cigarettes. Now, in most other areas that we're dealing with, even ones where there's a lot of data, we've got a whole range of different ways in which the outcomes are expressed. So, for example, with the work that I mentioned a bit earlier that we're doing, which is the other extreme, we're looking at driving patterns, and we're looking at speeding behavior. And that can be represented in lots of different ways, measured in lots of different ways, often quite idiosyncratically and bespoke. Now, the question is, how can you use those multiple versions of an outcome with a machine learning system to create the kind of thing that we've done with smoking? And this is a challenge for us, but one of the ways of doing it, which we're exploring at the moment, is to say, okay, you might have used a rating scale of how often do you speed or exceed the speed limit, or someone else might have used a study which is, what is your average driving speed? What you can do is take it at a higher level of generality in terms of the ontology and say, let's think of this just as fast driving. And let's code the data in that way, and then let's use machine learning to predict that more general outcome. It's not as good as if the data, were collected in a more systematic way, but it is what it is. It means you can get what you can get. And I think one of the key things with machine learning is it'll maximize your use of whatever data you've got. So if you don't have that much data, it'll maximize that. If you've got a lot of data, it'll maximize that. But you always have to consider the conclusions with respect to the, in terms of your confidence, with respect to the data that you've got. So the two limitations I would say are, one is you want as much data as you can get, and that takes a lot of time to code, and you need the studies. But you also want to try and get as systematic outcomes as possible. But with all that, and with the other advances in AI, I think we can really start to motor with this kind of approach.
Thanks, Robert. There's lots and lots of questions. So if we can keep answers fairly short. There's one about the accuracy of it, Robert, of this prediction tool. There's another one, anonymous attendee. When ontologies encoding behavior change scenarios, the basis of the AI or algorithm, then it is highly relevant how behavior is coded and the ontologies are coded. However, behavior in context could be coded in many ways, e.g. smoking behavior could be smoking, addiction, public, health, aware. How can ontology capture this ambiguity and get to a rich, deep understanding? And which is exactly the point of ontology. So, Robert, do you want to very briefly answer those two?
Yeah. Very briefly, the accuracy, there is the paper is in the Wellcome collection showing the accuracy of the tool. It is always going to be limited by the data that goes into it, and it's possible that a computer science student could come up with a better model that does a better job. That's a challenge for you. That's open access data, but it is quite accurate. It is pretty accurate. It's sufficiently accurate, I think. It certainly does better than other approaches, and it's sufficiently accurate, I would say, if you're developing a new intervention or putting an intervention into a new scenario, to give you a really good steer as to what you should put into that intervention for that particular group. So I would consider it hypothesis generation at this stage, not to give you a definitive answer in terms of the exact probability of success, but it's actually worked out quite accurate. And then very briefly on the second point, this is really where ontologies come in, because ontologies are in semantic hierarchies, and they are in hierarchy. They use classes that show formalized relationships with other things. So what that means is that, yes, if two people have got a somewhat different construct that's being measured or used, and you want to generate some conclusions about whatever those constructs have in common, you can go up a level in the semantic hierarchy and formulate and do your machine learning on that higher level.
Thanks, Robert. Jana, if you could pick one, but while you pick one, I've got one from Dougal saying about, have we thought about integrating risk of bias assessments for studies and data sets, contributing to the prediction tool? And if you remember the ontology that I showed you at the beginning, just the upper level of it, there was the blue scenario, but on the left was the red, which was about characterizing study methods. And yes, risk of bias assessment is in that, but we are developing that in the follow-on NIH-funded project called Apricot, which you can find in the Human Behaviour-Change project website, because we've merged the two, but we'll be developing this side of the ontology. So this is all work in progress. We have another 4.5 years funding if it doesn't get cut by NIH. So watch this space. Jana, over to you.
So I'll pick up one or two of the brief ones. So one question from an anonymous attendee is, how did you come to the decision of which rules to apply? And here the answer is, we learn the rules. It's part of the machine learning part of the overall AI approach, that we start out with, let's say, a completely random, long list of all possible rules that could be applied. And then the system narrows it down through a machine learning approach to the most predictive, relevant, and informative rules. So we learn the rules. Another question from anonymous attendee, and I'm not sure if it's the same anonymous attendee or a different one, is aside from smoking cessation, has this approach been used for other behaviors of interest? And the answer is not to our or my knowledge, at least not yet. I think it is still not trivial to assemble a data set large enough and clean enough to apply this kind of approach, and it takes funded researcher time, but we hope that it will become more and more easy to apply this kind of approaches, and then we can build up a whole suite of examples.
Thank you. Okay, I'm going to take one from David Shipworth again, which is about sort of interdisciplinary collaboration. He's making the point, it's very challenging and rarely results in methodological innovation, and asks, do we have any reflections on what it takes to make such programs work? I would say a couple of things. I mean, the first project that I was involved with, not as a PI, but was involved with between behavioural and computer scientists, we would turn up and the computer scientists would sit on one side of the table with all their Macs open, their white Macs open. And when we were giving presentations about the behavioural side of things, they would just do their programming or whatever they're doing. It was a very uninteractive project. So when I was putting the team together and I'd identified this group, actually 3 of us went over and spent a weekend in Dublin where the IBM research team were based, and spent an evening with them, dinner, having a drink. You know, are these people that we can connect with? So I think that's really important about collaborators. You know, are you speaking the same language? You know, do you share generally the same values and approach to research? So that was one thing. I think really spending the time to get to know potential collaborators, because often there's high stakes. The second thing is really to try and understand not only the different terms that are used, but also the different constructs that are used. So what we found working with computer scientists is that they didn't understand the words we were using and the way we meant them, and vice versa. So something we did very early on was agree to develop a glossary. And that glossary took a long time to put together, but you know what our shared definitions were. And it was also quite difficult to keep people on task, you know, say, computer scientists, hang on, we agreed that it would mean this. But that's well worth doing, you know, to really take the time. All of this takes time, but it's worth it. And the other thing is to recognize that different disciplines have very different ways of working. So with us, we always, I hope, produce protocols of what we're going to do, what we're planning to do. And we publish those. Open Science, we have a couple, I think, of webinars on open science. But this is incredibly important, to be transparent about what we do so that people can draw the right inferences from the findings. But what I found is our computer science colleagues, they don't work like that. You know, this was you know, novel and slightly anathema. And I do remember being in the pub with one of them after a meeting. That's the other thing. Make sure there's a good, you know, social side of any collaboration, I think. And the lead of the computer science team saying to me, Susan, let me explain how we work. It's like we have a toolbox and we have a problem and we rummage inside and see if there are any tools that fits our purpose. And if there's not, we invent a new one. And that's how we work. And that was very, you know, illustrative or very educational for me, because I had to take a step back and think, I can't get these people to work in the ways I work, and vice versa, but we need to understand how each other work, you know, in order to get the most from us. So we have 6 minutes left. Jana or Robert, are there outstanding questions you'd like to take before I wrap up?
So maybe I could take just one that I saw, which is about, let me just re-find it, from John O'Neill. For the tool, the smoking cessation prediction tool, would the newly published population ontology figure as an additional input for the prediction tool? Now here, the challenge is that the ontology alone is not enough as an input for the prediction tool. You also need ontology annotated data. So at the moment, despite there being a new ontology, there is not yet an updated version of the underlying data for the prediction tool. But if we could get that, then we will update the prediction tool with those additional parameters from the population ontology.
We're building as part of Apricot, a system for annotating using ontologies. And I think this is something that hopefully can be more widely used. And when it's done, people can improve on it and so on, and it'll be open source. It is so time consuming to do this annotation manually that we really do want to see advances in automation of this process. And we've still got a little way to go to achieve that. Interestingly, if you put it using generative AI, you can probably do a pretty good job if you use the right prompts of annotating behavior change techniques that are parts of interventions. They seem to do quite well at that. But a lot of population type stuff they struggle with, particularly when it comes to assigning numbers to parameters like mean age, things that we would find really easy to do looking at a PDF. Computers find harder to do. So there's work to be done there. But I think we're going to really need to beef up the automation of this.
Thanks very much, Robert. So our next and final in the series seminar is on 12th of May on socially responsible use of AI in behavioural research. And there's some questions asked today and before the seminar, which we can pick up then. So, for example, what are the biggest threats and greatest opportunities? We will address that. What do humans have to do to reduce automation bias within AI tools? We will definitely reduce that. There's a question today about qualitative research and bias, accuracy, and de-skilling using AI. We will definitely address that. And do send in any questions in advance that you'd like us to address within that. So as well as that, we will be developing over the next few months a repository specifically for AI tools and resources. But what struck me is there's been wonderful engagement, both last seminar and webinar and this one. I think there's a lot of interest in this area. I think there's huge potential for advancing behavioural research, and this is what BR UK is there to do, to really help that. And it's a very fast-changing world. And so one of the things I'm thinking, I haven't discussed this with Robert or Jan or anybody else, is that we might offer like a monthly surgery, which is an hour of literary Q&As where people could submit questions in advance and we can discuss issues that people have, developments in the field, etc. So that's just one thought to put out there, but we're forever having new thoughts about what we can do. Do contact through the website us to let us know what would be most helpful to you. But anyway, those are a couple of ideas. We'll definitely pursue the repository. We're definitely having a webinar next time, and maybe at the next webinar we'll let you know whether or not we'll take this idea forward. So thank you very much to Robert and Jana for great contribution, and also thank you very much to you for your fantastic questions, which really is what makes these webinars, because I know it's frustrating we can't have in-person discussions, but I think hopefully we get as good as we can get, given that we're all on a two-dimensional screen. So thank you very much, keep in touch, and hopefully see you at the next webinar. Bye.